Hello and welcome to another Robert's Tech video. Today we're going to talk about how to select a motor driver for your robot rover. Mostly just one important aspect, and that is the current rating for your motor driver. One of the things that you have to consider is the worst case current, called stall current, and that is the subject of today's video really. There are a lot of parameters you have to look at when you're choosing a motor driver depending on what you're building. It would be a subject of a very long video if you discussed everything you have to consider when driving an electric motor. But we're going to narrow this down to just a quick and easy way to how to select a motor driver that will work for your robot rover. So here we have three motor drivers. We have the very popular L298 motor driver that's available on eBay and Amazon, very inexpensive. We have a DF Robot motor driver, costs quite a bit more, has a lot more output capability, and then I have my own motor driver. So the Robert's Tech dual output driver. So what we're really concerned with in this video is the actual current rating of each of these, and then the motors that we're going to be using with them. So this one has a 2 amp per side. There's two circuits in here for two motors, and each one has a max current of 2 amps. The DF Robot, I believe, is rated at 10 amps, way over what we need, but it's a really good driver that I like to recommend. And even if you're not going to use the full output current, it's a very rugged, dependable driver to use. And then there's the Robert's Tech driver. This is rated at 3 amps on each output. So the question is, if I have a typical motor that I'm going to use for my robot rover, this one is a motor that I got off, I believe, Amazon or eBay, I can't remember. Has a built-in encoder. I've got a wheel attached to that, and I've got another one over here. This is a Gitterson motor. I do remember getting this one off Amazon. Both good motors for robotics. There's a lot of different motors out there, but this is the two that we're going to test today. So the main thing that I want to look at is, how do I know which of these drivers is going to be good for these motors? If you look up the specification for these motors online where I bought this, they're going to tell you the running current. So if you look at the specifications, we have voltage rating 12 volts, gives you the gear reduction, RPM, and then here's the rated current, 0.92 amps. So 0.92 amps, less than an amp, and you would say, okay, fine. A motor driver like this would be just fine for that. It puts out 2 amps, and so we're well below that output. But that's not the full story. You need to know the stall current. The stall current of the motor is the highest current that that motor is going to draw. And you need to know that because if you stall the motor, and by stall what I mean is, let's say your robot rover comes up against an obstacle and the wheel stops turning and you have full voltage going to the motor, it's going to draw its rated stall current, and that's going to be much higher than the running current. So, and that can happen. So you got to be prepared for that with a motor driver that can handle that current, because if you can't, you could instantly destroy the motor driver. And I'm going to show you how to very quickly determine what the stall current is, so that you know which motor driver is going to be suitable. So for the first motor, you can see the meter on the power supply. I'm going to turn this up to about 12 volts, and then on my current meter here, we're going to watch the current. And I've got this motor turning, and I'm going to go ahead and I'm going to grab this wheel and I'm going to stop the motor. And it's not easy, but you can see it goes up just below 2 amps, right about there. So that is my stall current. almost 2 amps with this motor, and that's the current you need to use to consider what size driver. So again, it tells me this one in theory would be fine for that, and any of these would work because this is a 3 amp, this is a 10 amp, this is a 2 amp. So that's the stall current for that motor, and any of those drivers would work for that. In theory, there are other considerations, but for the type of robot rover we're going to be building, I think that's enough to know. There's some other things to consider that we're going to talk about in a minute here, but I'm going to show you my next motor. Get this one plugged into the power supply. Okay, I've got the next motor on the power supply. Go ahead and turn this one up to about 12 volts. And then we're going to stall this one. And that one went all the way up to 3 amps. So you can see, it draws quite a bit more current than the other motor. Even though they look very similar, both these motors are about the same size. Very similar in size, but this one draws a lot more current. So right off the bat there, you're gonna realize that under a stalled condition you could end up damaging a driver like this because you're going to go way over the current that it's rated at. Now the other option with this is, since this has a 2 outputs, you can actually parallel these outputs into a single motor, giving you a 4 amp driver, and that's literally what you would have to do to be able to use this driver with this motor. Because if your robot rover again comes up against an obstacle and this wheel gets stuck, this is going to get fried if you're only using 1/2 of the circuit. With my driver, you'd be right at the limit of what it can handle. It would be okay, but it's possible it would go into overload condition and shut down, which is resettable, but that's a consideration. If you don't want the driver to shut down all the time, every time you come up against an obstacle it stops the motor, then you got to be aware that running this up to its limit, my board has an automatic shutdown that will have to be reset by the processor, and that can be written into code to do that. It's not the end of the world. So if the robot rover were to come up against an obstacle and stall out, the controller for this board would detect that and simply send a reset, and you'd be on your way again. With a DF robot, not sure what this one does on an overload. I'd have to look that up, but every board is different. Mine has an automatic shutdown. I know this board does not have an automatic shutdown, and I'd have to check with the DF robot. So that's the quick and easy way to measure stall current. I'm going to show you one other method, because you may not have a power supply like this with a current meter. You're probably going to have a meter like this. I'm going to show you the alternate setup here. So let's just say you have the battery for your project, and it could be a battery like this, which is what I use in my rovers. It could be an RC car type battery. Could just be some regular old batteries in a battery holder. However you're powering your robot. So you're going to have that as your power source, and then you may have a meter like this to read your current. So there's a couple things to consider here. One is, whenever you have a battery that you're using for a test like this or in your rover, be sure you have a fuse. Don't ever run a battery without a fuse. This particular battery can easily short circuit 100 amps into whatever you're driving. Every battery is going to be different. A lithium battery especially, you have to be very careful with. They can put out a lot of current and have been known to start fires when they get shorted out, so you got to be very careful. Always have a fuse when you're working with the battery. Next, the meter. So the meter has, most of these meters these days have a current position. Put it all the way down here to amps, and you move your probe lead over to the amps position. So now we can measure current. Now this is rated, most of these are rated up to 10 amps, and so we've got plenty of capability there. Just be aware that this is internally fused, which is fine, that's for safety. We got a fuse here, so that's good. But if I were to short this out in any way, I might blow the fuse in here. And the fuses in these things are pretty expensive. They're special safety fuses, so you want to be real careful you don't blow the fuse in your meter, or you're going to be putting out some money to replace that. That's also making sure when you're done you put this back over here, because that's how everybody blows up those fuses, trying to measure voltage on their current. So be sure to get it back over there when we're done with the test. Okay, so we've got our meter hooked up to our battery through a fuse. We're going to go ahead and connect our motor that we just did. This is the motor that was drawing 3 amps. I'm going to go ahead and hook it up, and I'm going to do this in typical fashion like you might do on your bench, and like I do a lot of the times. I'm going to use alligator clips. I'm going to hook it through my meter leads. I'm going to go ahead and put this together, and it'll start up. So it's running and running off the battery. You can see the running current here, about 137 milliamps, so 0.13 amps. And then I'm going to stall the motor, and there's 2.7, 2.6. So you can see the total current there, 2.5 amps. So why was it a little lower than what we measured on the power supply? That's because of all this wire. We've got so much wire in here. We've got banana clips. We got, 3 feet of leads. So the stall current there might be lower. We got a good one that time. Went over 3.3 amps that one time there. You got lucky. So, but you just have to remember, with all this wire, you're going to get a voltage drop that's going to maybe lower your amount that it really should be at. So just be aware of that, and just realize that if it gives you 2.7 amps, you probably should round that up to 3 amps. So that's how you might check for your stall current, and that'll help you in selecting your motor driver. Another thing I want to tell you about is when you do connect up your motor driver to an Arduino type processor, whatever processor you're using, there's one more thing I want to talk to you about, and that is how to couple the processor board to the motor driver. Bring over here. Got an Arduino right here also, sort of like an Arduino. Typical processor board. So when you connect your processor board to your motor board, we've all done this. We simply run the wires straight across, and then we have our connection that we're working with, and that in most cases works just fine. But you have to be aware that when you're driving a motor, especially through this type of motor driver, if the motor ever does get stalled, so again we're still talking about stalling, it will generate a tremendous spike back through the motor driver. That also happens when you start up the motor the first time, because starting the motor for the first time is also a stall. You don't think about that, but when you first place the voltage across the motor leads and the wheel is not turning, that is an instantaneous stall, and the motor will draw the full, in this case 3 amps, for a very short time until the wheel starts turning. So you're going to get stall currents even if you never stall the motor, just by starting it. Now, normally on these boards you'll have catch diodes, or what they call freewheeling diodes, that will handle spikes that come out as a result of stalls or starts, and they will limit the output voltage to the power supply voltage. But what's the power supply voltage? It's 12 volts on this unit. We're using 12-volt battery. What's the power supply voltage for your processor board? 5 volts or 3.3 volts. So if you have spikes coming from your motor, they're 12 volts, that could, in certain situations, feed back through your inputs and end up over here on your microcontroller and will fry your GPIO pins. And that has happened to me more than once. Usually it's under a situation where I was probably using a motor that was pushing the limit of the driver. It got stalled, or when I started it up under heavy load, a spike came through and just went straight through to my Arduino and fried it. And I've had that happen to me at least a couple times. I've learned my lesson the hard way. So what do? There's a couple things you can do, and I got a little diagram to show you. One way is optical isolation. That can add a lot of complexity and cost, and in most cases is overkill, but that's how it's done in high-end motor drivers most of the time. There are other methods, but this is probably the easiest, cheapest method, would be some sort of opto isolator. Just be aware when if you want to go this method, and I wouldn't unless you really got a really high-end, high current motor out here, and you got to protect this thing from some pretty nasty spikes. But if you do go that way, just be aware that a lot of optocouplers are too slow. Their switching time just is too slow for pulse width modulation square waves. So I would recommend something like the TLP250, which is a high-speed driver usually used to drive FETs in motor driver applications. So just be aware of that when you're choosing something like this. I've drawn this like a standard optocoupler. This is not the wiring of a TLP250, but just so you can see the theory behind the fact that you've got this isolation barrier that protects your Arduino from any spikes that may come back through from your motor driver. So that's one option. A simpler way, and I would highly recommend doing this with any setup you have with an Arduino or other processor board and a motor driver. It doesn't hurt to add it, even if you don't think you need it. Very low cost, 100 ohm resistor and a Transorb diode. Now Transorb is the trade name, kind of like Kleenex. It's actually an avalanche diode. This one happens to be a P6KE 6.8, which means it's rated at 6.8 volts. And this will protect the Arduino from any spikes that come back through. It will limit to that 6.8 volts around there. You have to look at the data sheet for all the actual clamping voltages and everything. But that's a low enough voltage that the Arduino will survive if a pulse comes back through here. Now you combine that with this 100 ohm resistor to limit the current that will get generated when this thing clamps, and that protects both the motor driver and the Arduino from excessive currents that might get generated. So again, the motor driver is running 12 volts. It can generate 12 volt spikes with these diodes in place, and then that could feed back into the Arduino. So with this 100 ohm and this Transorb diode, that will protect your Arduino from those. Now with something like the DF Robot board, I believe he's probably already got, I don't know how the schematic to this, but I'm fairly certain he's already got full protection from this end to that end. And you're going to be fine with this one. Mine already built in. I've already got those resistors and diodes in place, and so you're okay with that one. So this is the one you really have to worry about. Any other low-cost drivers, there's really no protection built into this thing for protecting your processor board. Okay, so that's our video for today. Thanks for tuning in, and we'll see you on the next video.